All right, so the first pitfall in feature engineering that we will address is redundant features. You can introduce a redundant feature by taking any linear combination of existing features and using that as a new feature. You might do that if you were, for example, changing the units or adding an offset to an existing feature, or maybe combining features in some interesting way, maybe taking the average of multiple columns. That would also be a linear combination of existing features. So in this notebook, we'll work through a simple example where we've just taken one of the feature columns x and just duplicated it. So let's do that. So we could define a feature function feedup, which will duplicate the column, and it'll also add the ones column, just as we've done in the past. So if we apply this function to our x, we get a matrix which has the ones column as well as the original x and then the copy of that x. Now, when we go to try to solve the normal equations passing in this matrix, we're going to get an interesting error. So we get an error that the matrix we're trying to solve, this system of equations we're trying to solve, has a singular matrix. Now, why is it a singular matrix? Well, it's a matrix that we can't invert, and we can't invert it because it's not really full rank. And we can actually look at that. So if we take the phi dup transpose times phi dup, we see that it is a 3 by 3 matrix corresponding to the 3 columns in our original phi matrix. And we also see that if we take the rank of this matrix, the rank using the NumPy linear algebra matrix rank function is actually rank 2. So it's deficient because we have this redundant column in the redundant column in our phi matrix. So these are not linearly independent columns, these two columns here. And so the rank of this product matrix is rank 2 and not rank 3. Right? So we can't invert a rank 3 matrix. Another way to think about it is that actually there's some redundancy. There's more than one optimal solution to this problem. You can think of it this way. We have two variables in our system of equations. Let's call that theta 2 or theta 1 and theta 2 that have interchangeable values. And to see why that is, what we can do is we can take the original theta hat line and we can use the optimal solution for the simple 1 and x feature matrix, one we used in the earlier video. And then we can copy that over, setting the theta 2, this last theta parameter, to 0. So it's essentially ignoring the redundant column. So that is one parameterization, and that will achieve the same accuracy as the original theta hat line model the original model in the previous video. Now, we can also ignore the middle copy of x. So this is the first copy. We can set that feature to 0, or that theta parameter, which essentially ignores that feature. So we set that to 0, we ignore that feature. And then we copy the optimal theta parameter for the second copy of x. So both of these will produce the same predictions as the original simple linear model we computed in the earlier video. And in fact, any convex combination of these two parameters for this three-dimensional or three-feature model will actually produce the same loss. So we can define a convex combination as taking the theta A and theta B, and then some alpha between 0 and 1. And let's say alpha is 0.2. So we'd say 0.2 of the theta A plus 1 minus 0.2, or 0.8 of theta B. That is a convex combination of theta A and theta B that produces yet another parameter value, which will perform just as well as as either of these parameter values or the original just two-dimensional model where we just had a intercept and slope. So we compute this convex combination, and I'll try a range of values between 0 and 1. I'll try 10 different possible values for that convex combination, computing the squared loss of the prediction of the model where I've taken a convex combination of theta A and theta B. And we see that all of these losses are essentially equivalent up to numerical precision, right? So any convex combination of these two parameterizations is equally good. And so there isn't really a clear optimal solution to this linear system of equations. Now, in a later lecture, we'll deal with regularization, and that will address this particular problem. But it's worth knowing about this when you go to build new features. You need to consider whether or not you're essentially constructing just a linear combination of existing features. It won't improve the accuracy of your model, and in some cases, it will actually make it difficult to solve the system of equations.